This video is supported by Brilliant.org. Imagine you're an explorer, and you're setting off across an unexplored continent for the first time, like Lewis and Clark or something. When you get deep into the woods, you enter an area that things don't work right. If you drop something, it falls upwards. Fish walk on land, sun rises in the west, trees grow sideways, just the way everything's supposed to work, it just doesn't here. This is the world the physics community found themselves in at the turn of the last century. As they cracked open the atom and looked inside, nothing made sense anymore. Nothing worked the way that physics had worked for hundreds of years according to Newtonian physics, and not even according to the new relativistic physics that Einstein had just popularized around the same time. Some of the brightest minds in the world, maybe of all time, argued on this problem, and what they wound up kind of settling on was this idea that at the smallest particles, things only exist in probability states that are really only understood by super advanced math. There was, however, another interpretation, one that's a lot closer to the classical physics that we all experience in daily life. All it required was invisible waves permeating the universe. When I was a kid, I played Little League Baseball like a lot of kids did. Mostly played shortstop, out in the outfield, couldn't hit a ball to save my life, but for a short period of time, I was a pitcher. Okay, I was a backup pitcher, but I did one time strike out Cody Dixon, so pretty awesome. But the point is, with enough practice, I developed the coordination and the muscle memory to where even if I scaled down the baseball to something smaller, like a tennis ball or a golf ball, maybe even a marble, I could still be pretty accurate with it, because even though the weights and the sizes were different, it still had the same physics involved. If I keep scaling down though, eventually it will get to the point where I can't be accurate with my pitch anymore, and not just because I can't see the object anymore, but because it actually operates in an entirely different set of physics. At the smallest measurable scales, there are totally different rules governing how particles interact with the environment. Rules that are puzzling and downright contradictory sometimes. A perfect example is wave-particle duality, which is illustrated in the double slit experiment, which I talked about here. The TLDR version of it is that photons, the very smallest packets of light, operate both as waves and as particles, depending on how you measure it. So you measure it one way, it will look like a wave. Measure it a different way, it'll look like a particle. Which is kind of like finding out that you weigh different on a scale if you're doing a handstand as opposed to standing straight up. That just makes no sense. When scientists started observing this phenomenon, of course, it just threw them for a loop. Like nothing in their bag of tricks explained this. They had to actually, it wasn't just about coming up with new theories, they had to come up with a whole new set of physics. And these interpretations roughly fell into two camps: instrumentalism and realism. The standard interpretation of quantum mechanics is instrumentalist. It basically says that this phenomenon can't be understood using physics, at least the physics that we use today. It says that the results of quantum experiments explain the circumstance behind the experiment, but not the process that produces the result. It kind of embraces the fundamental randomness of reality. But the realists don't embrace the randomness. They think that this can all be explained by classical physics, but the variations in our results just come from the fact that we're missing something. You know, like the way that we need dark energy to explain how the universe works in the biggest scales, we kind of need something else to explain how it works in the smallest scales. And that thing that came out of the realist camp is known as pilot wave theory. It's also sometimes known as de Broglie-Bohm theory or Bohmian mechanics. This is a way of trying to find whatever it is that missing something is and why it works the way it does. And it's easy to see why some people prefer this interpretation. It works a lot more like the classical mechanics that we all understand, and it's gotten a little bit of a resurgence in the last decade or so. So it might be worth our time to take a look at the universe that pilot wave theory describes. In this universe, particles actually exist in real 3D space at all times, as opposed to the Copenhagen interpretation, which I've talked about previously on this channel, which basically says that everything exists in a probability state and in a bit of a waveform until you measure it and then the waveform collapses. In Copenhagen, the measurement is what defines the particle. In pilot wave, the particle exists whether you measure it or not. In this theory, particles do still behave like waves, but they do so because they're actually being acted on by an invisible wave that we just can't perceive. You know, going back to baseball for a second, if I showed you a photo of a baseball in flight, you could see that the baseball was there, but without any other visual cues, you wouldn't be able to determine things like motion or speed or anything like that. And it's similar with the wave. If you just took a picture of a particle, you wouldn't be able to tell that there was a wave acting on it. But if you took several pictures in a row and had those visual cues, you could see the action of the wave on the particle. You know, it might be moving by influences that I can't know precisely, but you can see the effect those influences have on the particle. Now this means in a pilot wave universe, the change in a particle's position is deterministic, as opposed to the Copenhagen interpretation, which is stochastic, meaning it kind of embraces that randomness I was talking about earlier. But the math comes out the same in both of them. You get the same range of possible outcomes in pilot wave theory that you get in the standard interpretation. And this is no accident, because these were developed at the exact same time. Pilot wave was birthed by Louis de Broglie, and the Copenhagen interpretation was developed by Niels Bohr and Werner Heisenberg, who were from Copenhagen, hence the name. These guys came to the problem with a different perspective, but they use the same mathematical concepts. And the battle royale that decided between the two ideas was the Solvay Conference in 1927, where Einstein battled with Niels Bohr saying, "God does not play dice with the universe." Regardless, the Copenhagen interpretation won out, and even de Broglie conceded defeat. And pilot wave theory would be almost forgotten for about 30 years, until David Bohm rediscovered it in the 1950s and expanded on it. He took de Broglie's work and derived equations out of it that brought it more into line with the contemporary experiments that were being done at the time. And thanks to his work, to date, no experiment has produced results using the standard interpretation that couldn't be described and explained by the pilot wave interpretation. In other words, as far as experimental confirmation is concerned, no interpretation wins out, really. Up to now, I've managed to avoid talking about wave function, but let's go ahead and do that, shall we? In both the standard interpretation and pilot wave theory, the wave function is a mathematical formula that gives the probability of finding a particle in a certain position. In both cases, we talk about probabilities, but in the standard interpretation, we talk about probabilities because everything is random and we don't know where it's going to be. But in pilot wave theory, we talk about probabilities because we don't know exactly the influences that are working on the particle. So the wave function gives the same results whether you believe that a particle fully exists before measurement or not, but at the time of measurement, that's a different story. In standard interpretation, the wave function collapses. Since the wave function was describing pure randomness, when you take a measurement and the randomness disappears, then the wave function disappears. This is not the case with pilot wave theory. In pilot wave theory, the starting position is real, the particle is real, the wave acting on that particle is real, and they're real after the measurement is taken. So since the wave does not cease to exist, the wave function doesn't collapse. So with Bohm taking the baton from de Broglie, pilot wave theory made some huge strides, but there was still one issue to resolve, and that's the issue of locality. Now, I've talked in previous videos about quantum entanglement, the idea that two different particles can be connected and transfer information to each other back and forth over time and space faster than light can travel, which Einstein hated so much that he called it spooky action at a distance. So yeah, another way of putting that is that quantum information is non-local, meaning that there's a universal wave function, a wave function that's universal in scope through space and time. Now, in quantum experiments, it's sometimes useful to draw an imaginary box around a particle or a system of particles. Mathematically, there's a wave function for the particle or system inside the box. This is called a subuniversal system. And when a subuniversal system is measured, the wave function of the system collapses, but not the universal wave function. And for much of the 20th century, there was a debate about how big a box an experimenter would have to draw to take in all possible influences. For Einstein, this was determined by the speed of light, because relativity prohibits information moving faster than that, which is why he was big on locality. Unfortunately for Einstein, many experiments have proven him wrong. Einstein didn't like that. Being right was kind of his thing. Physicist John Bell is the guy who resolved this issue, and he proposed an experiment in 1964 that has since shown that no comprehensive theory of quantum mechanics can be strictly local. And since the wave function of pilot wave theory is universal, that means that its influence is non-local, so we can kind of resolve the paradox without destroying relativity. And this might be a good time to talk about today's supporting sponsor, the Brain Bucket. Brain oozing out of your ear? Don't waste it. Get a Brain Bucket. It's clean, it's simple, it's easy. Brains are greasy and stain your shirt. Yuck! With the Brain Bucket, you can collect those brains before they ever reach your shoulder. You can use the brains as a fun toy for kids, stain your deck, or make a delicious brain stew. The Brain Bucket. Get yours today. Anyway, those are the basics. All in all, I think pilot wave theory is an interesting way of looking at the quantum universe, but of course there are objections to this viewpoint. One is just simply that pilot wave theory adds complexity in math without actually predicting anything that's not predictable outside of the standard interpretation. And this is true. If you're only interested in calculating predictions, the standard model works just as well as anything else. It's when you get to looking at what this says about the universe that things really start to become more drastic. In what sort of universe do these accurate predictions make sense? Is it random? Is it deterministic? Is it local? Is it non-local? Lots of questions get brought up here. The standard interpretation kind of shows us snapshots of the universe that we live in, whereas Pilot Wave tries to arrange those snapshots into a movie. And another objection is that Pilot Wave theory is too classical. You know, it's too much like the world that we live in than the experiments would show. And this was of particular concern in the early days of quantum theory, when the only way that seemed to be right moving forward was to make a break from the classical world. In fact, you may have seen some videos where people have modeled Pilot Wave interactions in a bath of silicone oil. And these do a good job of sort of simulating the results of Bohmian motion, but they don't really encapsulate the universal wave function idea. And also, Pilot Wave theory doesn't take into account things like spin and angular momentum, which appears at the time of measurement in the standard interpretation. So there are still some functions of a particle that aren't deterministic. So it leaves some gaps in Pilot Wave theory there. But no valid objection has completely shut the door on the idea that particles are real physical things that are worked on by a pilot wave. And there are some scientists that are working on some new advancements in this. I'll put some links down in the description. Now, obviously, this is a complex topic, one that I only barely understand, but no, I'd love to hear what you think in the comments below. You know, do you think the universe is just a mess of random possibilities, or is it an actual physical thing worked on by invisible waves? Talk about it in the comments. And if you want to go deeper into the quantum realm, you are in luck, because you can check out the course Quantum Objects on Brilliant.org. This ever-growing class features problems that walk you through the basics of particle spin, the math behind quantum objects, and quantum mechanics, with more on the way. And if you haven't checked out Brilliant, it's really worth a look. Brilliant's an online learning platform that uses our natural human aptitude for problem solving to teach complex scientific topics in a way that makes sense to you, so you can apply them to other parts of your life. Brilliant also features daily problems, little questions that you can solve on a variety of topics so you can build a daily learning habit. Sign up for free at brilliant.org/answerswithjoe, and you can get access to their weekly puzzles and brain teasers to kind of give you a little nugget of what's going on. And the first 200 people that sign up for the premium subscription, which gives you access to every single one of their courses, gets 20% off your subscription for life. It's fun, you'll like it. Brilliant.org/answerswithjoe. Links down in the description. Big thanks to Brilliant for supporting this video, and a huge shout out to my answer files on Patreon that are supporting this channel, keeping the lights on, building a great community, and helping me out in so many different ways. I love you guys. There's some new people I want to shout out real quick. We've got Christopher Nostrand, Steve Dowdy, James Wenzel, Sayonara, clever, Kelly Mullen, Derek Boyd, James Inall, Paul Garrett, and Ricky Downhill. Thank you guys so much. If you would like to join them, get access to cool perks like early access to videos and just behind the scenes stuff, you can go to patreon.com/answerswithjoe. Please like and share this video if you liked it, and if this is your first time here, maybe check out this video, because Google thinks you'll like that, or any of the other videos that might be on the little side over here. I talk about cool science nerdy topics on Mondays, more random topics on Thursdays, and if you like any of those, please do subscribe, and then you can be first in line to see them. T-shirts, as always, available in the store, answerswithjoe.com/shirts. Go check those out. Thanks again for watching. You guys go out now, have an eye-opening week, and I'll see you on Monday. Love you guys. Take care.